Welcome to this explainer. Today, we're diving into something absolutely massive. We're going to uncover the hidden engineering magic behind those giant horizontal structures you see powering global industries, from oil refineries to massive chemical plants. These aren't just static chunks of metal, they are dynamic, shifting giants. And understanding how engineers keep them safely on the ground is absolutely fascinating. So, I want you to think about this core engineering paradox for a second. Usually, in construction, when you want to secure something, you bolt it down as tightly as physically possible, right? But what on earth do you do when you need to tie down a piece of heavy equipment that literally refuses to stay the same shape? How do you secure a moving target? To understand why it changes size, we gotta look at the extreme conditions inside these plants. When these steel giants actually go into operation, they're processing fluids and gases at just blistering temperatures, often reaching 300 degrees Celsius or even higher. And that intense sustained heat, well, that triggers our invisible enemy. Now, to a beginner walking onto a construction site, a 50-ton suspended machine like this just looks like a giant, impenetrable steel cylinder. I mean, it looks like it could survive a direct meteor strike without budging a single millimeter. But, physics tells a very different story. The secret here lies in thermal expansion. When the plant powers up, all that intense internal heat transfers directly to the metal shell of the equipment. And as metal heats up, its atoms start vibrating and pushing further apart. The result? The entire machine physically grows. It actually gets longer. Let's break this concept down really simply. If you take a massive horizontal cylinder and you bolt it down completely tight on both ends, what happens when it heats up and tries to expand? That metal has to go somewhere. If it's trapped, the thermal stress just builds and builds until the machine literally bends, rips itself apart, or completely shatters the solid concrete foundation it's sitting on. So, how do engineers actually solve this massive problem? Well, they don't fight physics, they accommodate it. Instead of locking the machine down rigidly on all sides, they brilliantly design the equipment to sit on two very distinct, very different foundations at either end. It all comes down to these two saddles. On one end, we have the fixed saddle, which acts as your typical rigid anchor. But the other end features what we call a sliding saddle. And this is engineered with oval, slotted holes. So instead of a tight circular hole, it's an elongated oval. This actually allows the heavy machine to horizontally breathe and literally slide along the concrete as it expands from the heat. But hey, knowing the design is really only half the battle. Now we actually have to get this massive piece of steel safely onto those foundations. This brings us to the erection phase. And no, we're definitely not just dropping it into place and hoping for the best. This requires heavy equipment, massive cranes, and just absolute pinpoint precision. This high-stakes lift happens in three very precise steps. First up, perfecting the rigging to find the exact center of gravity so the equipment doesn't tilt dangerously. Second, those massive cranes take the full weight. And finally, workers painstakingly guide those massive steel feet down onto the waiting anchor bolts. Now, you might be thinking that once the giant is lowered onto those bolts, the job's done, right? Actually, not even close. It isn't perfectly flat yet. In industrial engineering, a tilt of even a single millimeter can cause pumps to fail and pipes to crack. We need extreme precision here. We're talking micromillimeter leveling. To achieve that kind of perfection, we use a bit of a secret weapon, shim plates. Think of it kind of like shoving a folded up piece of paper under a wobbly restaurant table, but, on a massive industrial scale. We don't just pour concrete and cross our fingers that it dries perfectly flat. Instead, we use these precision-machined, incredibly thin metal sheets to adjust the exact height and level before we lock anything down. To the untrained eye, these little guys just look like sheets of aluminum foil. But they're actually high-strength stainless steel plates, precision manufactured to fractions of a millimeter. And incredibly, they are strong enough to support a machine weighing tens of thousands of kilos without crushing. Out in the field, workers meticulously insert these U-shaped plates right around the anchor bolts, directly under the equipment's steel saddles. They slide them in, literally millimeter by millimeter, constantly checking their high-precision levels until the entire behemoth is sitting perfectly, flawlessly horizontal. Okay, so once our giant is perfectly leveled, it's finally time to lock it down. But wait, remember our invisible enemy? Thermal expansion? We have to go back to that sliding saddle, the side specifically designed to handle the heat. The final securing process over there is honestly a delicate art form. Here's exactly how it's done. First, they insert low-friction slide plates. Think of materials like Teflon, so the heavy steel can actually glide smoothly. Next, they align the bolts perfectly inside those oval slots. Then comes the wildly counterintuitive part. You have to leave the nuts strictly hand-tight. If you crank them down with a wrench, the machine can't slide. And finally, they have to completely destroy and remove any temporary shipping brackets. If you forget that, you'll accidentally lock the whole machine in place. The stakes here are astronomically high. If a crew forgets to leave those nuts hand-tight, or if they misalign the slotted holes, or even just leave a single temporary shipping bracket attached, well, the plant will power up, the machine will heat up, and it will forcefully shear those thick steel anchor bolts right out of the solid concrete. Precision at this stage is literally the difference between decades of smooth, profitable operation and an immediate, catastrophic disaster. It's honestly amazing to realize that these towering, incredibly heavy monuments of steel are actually dynamic, shifting structures carefully engineered to move and breathe. So, the next time you drive past a massive industrial plant with all its complex pipes and vessels, I want you to ask yourself, which direction are those giant machines breathing right now? Thanks so much for joining me on this explainer, and keep looking deeper into the incredible world built around you.